In this video, we are looking at question number 34 from GATE Biotechnology 2021 paper. So the question is, the tertiary structure of a protein consisting of alpha helices and beta strands can be determined by option A, circular dichroism spectroscopy, option B, mass spectrometry, option C, nuclear magnetic resonance spectroscopy, and option D, UV spectroscopy. So before we answer this, let's look about each of these following techniques.
Circular dichroism spectroscopy.
The next technique is circular dichroism spectroscopy. So it is a form of light absorption spectroscopy which is used in determining molecular behavior in a broad spectrum of perturbation by measuring the difference in absorbance of light circularly polarized and left circularly polarized light. So light could be of different polarizations. So unpolarized light is where the direction of oscillations randomly changes in a same plane with time. And plane polarized light is when magnetic and electric field components oscillate in a definite plane being perpendicular to each other. And circularly polarized light is when magnetic field remains oscillating but electric field vector changes direction in a rotatory circular motion. So in simple terms, circularly polarized light is where the electric field is rotating and the magnetic field is oscillating left and right like this, denoted by the arrow marks, and the direction of the propagation of the light is this way. So this represents a circularly polarized light beam, and these shows the other form of polarized light. So linearly polarized light where the electric and magnetic fields oscillate and perpendicular to each other, and unpolarized light is where oscillation happens in random directions. Also, so where does this polarized light come from? So few golden crab beetle like Chrysnia gloriosa and a few mantis shrimp have been found to generate circularly polarized light. And further, the circularly polarized light can be categorized as right hand circularly polarized, which is clockwise and abbreviated as RCP, and left hand circularly polarized, which is anti-clockwise. Let's now look at the mechanism of action of circular dichroism spectroscopy. So electric field of a light beam causes a linear displacement of charge when it interacts with molecules. So the magnetic field of the light beam, on the other hand, it causes circulation of charge. So these two motions combine to result an excitation of electrons in a helical fashion. So but the radiation used being chiral, it interacts in different fashion with a definitely chiral entity. So after interaction, the electric field vector traces out an elliptical path. So circularly polarized light becomes elliptical polarized light. So here's a diagrammatic representation. So light sources like short arc xenon lamps, they emit the light, and white unpolarized light is passed through the monochromator and it gets linearly polarized. So the linearly polarized light then passes through the photoelastic modulator, and then this gives circular polarized light, both RCP and LCP, and this then passes through the chiral specimen which is under the experiment, and then finally it passes through the detector.
So what actually happens here? So when passing through an optical active medium, the speed between the RCP and LCP light changes along with the change in their wavelengths and their absorptivity. So now wavelength dependent difference of absorption is measured and plotted to get the circular dichroism spectra of the sample. So CD is measured by the the difference in between the absorptivity of LCP and RCP. So it's delta epsilon. So in some cases, apart from delta epsilon, which is the change in absorption between the RCP and LCP, molecular ellipticity theta is also measured. the relationship between delta, epsilon, and theta is given by this equation, where ER and EL are the magnitudes of the electric field vectors of the RCP and LCP respectively. So now what exactly do these values mean, and how does it tell anything about the structure of the molecule or the protein? So the circular dichroism signal arises from differential like RCP and LCP due to the chiral nature of the biomolecules. So the CD spectrum typically consists of two main features. So one is the negative band and the other is the positive band. So the negative band, the N band, is where the absorbance of left-handed circularly polarized light is higher than the right-handed circularly polarized light. It is often associated with a decrease in molecular elasticity and is characteristic of certain secondary structures. So when like the delta epsilon value is negative, it means that the molecule is less elliptical, like it's not very elliptical. And a positive band is where the absorbance of right-handed circularly polarized RCP is higher than the LCP. So it is associated with an increase in molar ellipticity and is also characteristic of specific secondary structures. So the shape and the position of these bands in the CD spectrum are indicative of the types and amounts of secondary structure present in the sample. So common secondary structures in proteins are usually alpha helices and beta sheets and random coils, like you all would know. And each type of secondary structure contributes differently to the CD spectrum, allowing researchers to analyze and interpret the secondary structure of the sample.
So this shows the spectrum of light, and so vacuum UV spectrum ranges between 100 to 200 nanometers, and near UV ranges from 250 to 350 nanometers, and near infrared 750 to 950 nanometers, and far UV 200 to 250, and the UV visible spectrum, it's the range of all the visible colors you can see along with the UV, it's 350 to 750 nanometers. So, like to give a more detailed explanation, far UV circular dichroism, which is 200 to 250 nanometer, is used to investigate secondary structure of proteins. Change in protein secondary structure as a function of temperature and concentration can be known, which allows us to know the enthalpy and Gibbs free energy of the process. And then near UV CD spectroscopy, 250 to 350 nanometer range. So this spectra provides information on the tertiary structure of proteins. It provides information on the nature of the prosthetic group present in the protein. And UV visible spectrum ranging between 350 to 750 nanometers in the visible region is found only when metal is in chiral environment, and free metal ions in solution are not detected by this visible range, and this can be used to detect protein bound metals. And further, near infrared CD with the range of the spectrum between 750 to 950 nanometer can be used to investigate geometric and electronic structure by probing metal DD transitions. Circular dichroism spectroscopy has several applications. So it's used to know whether the protein is folded or not, and if so, then the characterization of its secondary and tertiary structure and its structural family is identified. And then it's used to compare the structure of a protein obtained from different sources. And also, it's used to study conformational stability of a protein under perturbation of environment caused by heat, pH, denaturants, stabilizing agents, and so on. So it just helps to study the how stable the protein conformation is. And it's also used to study the effect of protein-protein or ligand-protein interactions. The advantages of this technique is that minimum quantity of sample is required, and it does not require extensive data processing, and it can be effectively used in the presence of multiple cofactors. It also has several complications and disadvantages. So carbohydrates cannot be easily studied in this method, and aqueous buffer system used in circular some spectroscopy often absorb in the range where structural features exist, and the system should be completely devoid of oxygen to perform the experiment below 200 nanometer wavelength of the light. And phosphate, sulfur, carbonate, and acetate buffers cannot be used until they are prepared in the range of 10 to 40 millimolars, and a large number of organic solvents cannot be used. And instead of ordinary xenon arc lamps, the use of high pressure short arc xenon lamps are essential for doing low UV series spectroscopy. Let's now learn about mass spectroscopy. So, mass spectroscopy is one of the primary spectroscopic methods for molecular analysis available to an organic chemist. So, it's a microanalytical technique requiring only a few nanomoles of the sample to obtain characteristic information related to the structure and molecular weight of the analyte. So, it is not concerned with non destructive interactions between molecules and electromagnetic radiation. Mass spectroscopy is the most accurate method for determining the molecular mass of the compound and its elemental composition, just as the name suggests. So, in this technique, molecules are bombarded with a beam of energetic electrons, and the molecules are ionized and broken up into fragments, and some of them are positive ions. So, each kind of ion has a particular ratio of mass to charge, that is m by e ratio, and for most ions the charge is 1, and thus the m by e ratio is simply the molecular mass of the ion. Mass spectra is used in two general ways. So one is to prove the identity of two compounds, and two is to establish the structure of a new compound. So the mass spectrum of a compound helps to establish the structure of a new compound in many different ways. So it can give the exact molecular mass, and it could give a molecular formula, or it can even reveal the presence of certain structural units in a molecule. So the basic theory behind mass spectroscopy is that it deals with the examination of the characteristic fragment ions arising from the breakdown of organic molecules. So a mass spectrum is the plot of relative abundance of ions against their mass to charge ratio. So the basic aspect of organic mass spectroscopy consists of bombarding the vapor of an organic compound with a beam of electron accelerated from a filament to an energy of 70 eV to form positively charged ions. The additional energy of the electrons is dissipated in breaking the bonds in the molecular ion, which undergoes fragmentation to yield many neutral or positively charged species. So, this fragmentation may result in the formation of an even electron ion and radical. So, the various positive ions formed can be accelerated and deflected by electric or magnetic fields. So, the deflection of these ions depends on the mass, charge, and the velocity. So, for a given charge, velocity, and deflecting force, the deflection is less for a heavier particle as compared to a lighter particle. So, thus, a number of beams each containing ion with the same m by z values are obtained, and the beams are then made to strike against a photographic plate where they don't not only appear as separate lines, but the intensity of each peak as a result of the bombardment is recorded. So, the clear visual presentation of a mass spectrum is usually obtained by plotting m by z values against the relative abundance, assigning the most abundant ion in the spectrum as 100%. So, that is the base peak. So, although organic mass spectrometry is routinely used along with infrared, NMR, and UV for structural determination, its basic theory is different from the rest of these techniques. So, in mass spectrometry, no characteristic selective absorption of radiation is involved, as in the case of these other three methods. And then in mass spectrometry, the compound undergoes irreversible chemical changes, unlike the others, where the changes are reversible physical changes. Like once the sample has gone through a mass spec, the sample cannot be reused. So the mass spectral reactions are much more drastic than usual chemical reactions.
It involves the production and separation of ionized molecules and their ionic decomposition product, and finally the measurement of relative abundance of different ions produced. It is thus a destructive technique in that the sample is consumed during the analysis. So, in most cases, the nascent molecular ion of the analyte produced fragment ions by cleavage of the bond, and the resulting fragmentation pattern constitutes the mass spectrum. So, thus, the mass spectrum of each compound is unique and can be used as a chemical fingerprint to characterize the sample.
So here is a diagrammatic representation of how the mass spectrometer in instrument looks like. So, and several steps of the whole process takes place in each of these different sections of the instrument. And so let's look at each of these methods, like processes: ionization, acceleration, deflection, and detection, in the next few slides. So the first step is ionization. So the atom is ionized by knocking one or more electrons off to give a positive ion. So mass spectrometers always work only with positive ions, and the positive ions formed will always carry a positive charge of +1. So these positive ions are persuaded out into the rest of the machine by the ion repeller, which is a metal plate carrying a slight positive charge. So the vaporized sample is passed through this inlet, and it is radiated with a beam of electrons over here, and the positive ions are emitted, and the positive ions, they do not go this way because of the ion repeller, which is also positively charged. So because like charges, they repel each other, the positive charges are like repulsed to the opposite direction, and hence the ions, they move out of this chamber and they move to the next part of the instrument. The next step is acceleration. So the positive ions, now they are accelerated so that they all have the same kinetic energy. So the ionization chamber, it has a voltage of like 10,000 volts, and the ion beam passes through this chamber. So the positive ions are repelled away from the positive ionization chamber, and they pass through three slits with voltage in decreasing order. So it starts with 10,000 volts and the voltage keeps decreasing, and at this third slit the voltage is 0 volts. So the middle slit carries some intermediate voltage. So all the ions are accelerated into a finely focused beam of ions. The next step is deflection. So the ions are then deflected by a magnetic field according to their masses. So the lighter particles are deflected more and the heavier particles are deflected less. So the amount of deflection also depends on the number of positive charges on the ion. So the more positive ions the ion has, the more it gets deflected. So like we just saw, the deflection of the ions depends on the mass of the ions and the charge of the ions. The next step is detection. So the beam of ions passing through this machine is detected electrically. So when the ions hit the metal box, the charge is neutralized by an electron jumping from the metal on to the ion. So as you can see here, the ion stream that is passed through the deflector, it makes through the detector machine. It makes through this the ion detector chamber. And here what happens is, so here's a positive ion, and other ions collide with the walls where they will pick up electrons, and hence the positively charged ion gets neutralized because an electron is knocked into it. So they get removed from the mass spectrometer by the vacuum pump. So this process, the neutralization of the positively charged ions, it leaves a space among the electrons in the metal and the electrons in the wire shuffling along to fill it. So a flow of electrons in the wire is detected as an electric current, which is amplified and recorded, and the more ions arriving, the greater the current is.
So, one of the processes that is involved in mass spec is fragmentation. So, the bombardment of molecules by the electron beam with energy between 10 to 15 eV usually results in the ionization of molecules by removal of one electron. That is the formation of molecular ions. So this is the first step of the whole procedure, which is ionization. So when the energy of electron beam is increased between 50 to 70 eV, these molecular ions acquire a high excitation, resulting in their breakdown into various fragments. So this process is called fragmentation. So as a result of fragmentation, several types of ions are formed. So they are molecular ion or parent ion, which forms the big peak in the mass spec reading, and then fragment ions, which result in smaller peaks, and also rearrangement ions, multi-charge ions, negative ions, and metastable ions. So by reading the peaks, we could know what molecule is present in the sample. So here are some general rules for interpreting the mass spectrum. So in order to interpret the mass spectrum, one should attain an understanding of the ionization process, and you should know how to observe the fragmentation pattern. So the exact molecular weight is the molecular weight of a pure compound from the identification of the parent peak. So the molecular weight one can determine molecular formula, and and then there's isotope effects. So heavy isotopes will exhibit peaks in a mass spectrum at m by z ratio, one or more units higher than the normal. So that indicates that there are isotopes of molecules present. So there will be small peaks at m plus 1 and m plus 2. For example, like for nitrogen, the molecular weight is 14. But if we see a peak at 15, it means that an isotope of nitrogen is present. So here's a simple readout from the mass spec. And so the x-axis denotes the mass by charge m by z values. So this format is used because a m by z ratio of 28 can represent a mass of 28 with a single charge, or it might be 56 with a charge of 2, because 56 divided by 2 is 28. So it could just indicate like two molecules of the molecular weight 28. So a single charge is the most common, so the x-axis best equates to mass. And then y-axis indicates abundance. So in a standard mass spectrum, the uh, the y-axis is made relative to the largest line, which is the base peak. So it will run from 0 to 100%. So the relative abundance would be 0 to 100%. So absolute abundances are typically used in GCMS spectra, which is like gas chromatography and mass spectroscopy. So they will run from 0 to the highest recorded line intensity. So those are absolute abundances, whereas in relative abundances, everything is normalized to the highest base peak. So what are the types of information you can get from this graph? So you could get information about the mass of the fragments and the presence of isotope lines and gaps between these lines. So let's look at some of the basic information. So here's a spectrum for air, which is like a mixture of nitrogen, carbon dioxide, and oxygen, but predominantly nitrogen and oxygen. So if you look at this peak, it's 28. So it would be nitrogen N2, which is 14 plus 14, 28. And also 29 could indicate N15, which is an isotope of nitrogen N14. So it is small because N15 is not very common in nature, because that is why you could see very less abundance of the isotope N15, but highest abundance for like normal nitrogen N14. So we know that most of the small lines could be because of the isotopes, but what could 16 and 17 be from? So these fragments could indicate water, and water shows fragmentation where it can lose one or two hydrogen atoms. So you'll see that the fragmentation patterns are very important for mass spectroscopy. So 18 would indicate water, H2O, because 16 plus 1 plus 1, H2O gives a mass of 18. So when you see 17, it could be OH, a hydroxyl group, where one hydrogen atom is lost, and 16 could indicate simply an oxygen molecule. Also, a peak up to 100% abundance is called a base peak, and M is a parent ion peak, which is usually the next largest peak to the base peak. It is also called molecular ion peak. So, molecular peak of M produced when an electron ejected from the molecule is M plus 2 electrons, a protonated M plus 2 electrons. And here are some of the exact masses and natural isotopic abundance and some ratios. So these are some values you could remember, like to easily interpret what mass indicates what molecule from a mass spectrum reading. So NMR spectroscopy has become one of the most frequently used analytical tools to elucidate chemical structures. So it is particularly useful for carbon-based chemical compounds, which are known as organic compounds, the molecules that make up all living things and many substances that we interact with on a daily basis. So, nuclear magnetic resonance is what uh, the full form of NMR is, and it's used to determine the chemical and physical properties of organic compounds and inorganic as well, but mostly organic compounds. So, yeah, the protons in the atoms of the molecules, they behave as magnets, and it repels and tries to rotate the other atoms present near it. So the NMR machine creates a magnetic field and directs this magnet, which are the protons, in whatever direction it is to the stable state.
Here's a diagrammatic representation of the NMR spectrophotometer.
The theory behind NMR comes from the spin of a nucleus, and it generates a magnetic field. So, without an external applied magnetic field, the nuclear spins are in random directions, as you could see here. But when an external magnetic field BO is present, the nuclei either align themselves with or against the external magnetic field. So, many nuclei undergo magnetic resonance. In general, nuclei composed of an odd number of protons, like 1H, the protium ion, and the isotopes of atoms like molecules like 14N, 19F, and 31P, or an odd number of neutrons like 13 carbon. All these show magnetic behavior and they're marked as active in this column. So, if both the proton and neutron counts are even, like 12C or 16O, the nuclei are non magnetic.
So it is the positively charged nucleus that NMR spectroscopy detects and gives us a lot of information about the overall structure of the molecule. So different nuclei have different spins, and the ones with spin 1/2 can exist in one of the two possible spin states. So these include the following atomic isotopes. The hydrogen nucleus, usually referred to as proton, and present in most of the organic compounds, and is the most frequently analyzed by NMR. The precision frequency or the Larmor frequency is given by this equation and is dependent on the strength of the magnetic field and the gyromagnetic ratio, which is a constant for a given isotope. So if you apply a short radio frequency pulse or RF pulse at the right angles to B0, the nuclei will flip down to the XY plane in unison and continue to precess. So let's represent the average magnetic moment of a set of nuclei by the sphere. So at equilibrium, the magnetization vector will be aligned along B0 as depicted here. And we have seen that the RF pulse will flip the magnetization vector to the XY plane. So the rotating magnetization vector induces a current in a receiver coil. So this signal is detected and amplified. So we can see that the oscillating signal sweeps out a sine wave with decreasing magnitude as the nucleus realigns with the magnetic field B0. So this wave is called the free induction decay or FID. So if each proton sweeps out an FID at the same frequency, then each proton would look identical and we won't be able to learn anything from the structure of the molecule. So this is converted to Fourier transformed signals, which gives us peaks in the spectrum. Let's consider two protons in different parts of a molecule, and each will be exposed to a different magnetic field depending on the electron density distribution. So the electron creates its own magnetic field which opposes the applied magnetic field B0. And a proton with a high electron density around it experiences a lower magnetic field and therefore a lower frequency. And a proton in an electron poor environment has a higher frequency. So typically protons in an electron rich environment are referred to as shielded, and those in an electron poor environment are referred to as deshielded. Aromatic rings such as benzene ring can induce their own magnetic fields, which can further modify the magnetic field around the proton. So now if we pulse these with an RF pulse, we will get two signals in our FID, one oscillating at a high frequency and one oscillating at a low frequency. The FID is a representation of the wave in the time domain. The Fourier transformation mathematically converts this to the frequency domain, which allows for a visual representation in an NMR spectrum, with the shielded protons giving peaks at the right side and the deshielded protons giving peaks on the left side. Here's a simple molecule with hydrogens in 5 different electronic environments. So each type of proton will experience a slightly different magnetic field strength and will precess at its own frequency, giving 5 overlapping signals in the FID. So after Fourier transformation, we will get a spectrum with 5 peaks, each peak representing a proton or a set of protons in a particular chemical environment. So with this spectrum in hand, we can start to deduce the chemical space around each proton. So we have seen that an isolated proton or a group of identical protons will give an NMR spectrum with a single peak known as a singlet. Sometimes you will also have protons that are close enough that their magnetic spin states interact. So this is known as spin-spin coupling. So in this case, the peaks do not appear as a singlet but rather appear as a split peak, as you can see here. So this is known as a doublet. For example, if a proton A has a neighbor proton B in a different electronic environment, proton A will be affected by its neighbor, and proton B will either be aligned up or down. Thus, proton A will be a doublet. So likewise, proton B will be split by the proton A, and it will be a doublet as well. And two neighboring protons will give a triplet, and 3 neighboring protons will give a quartet. So you can even see quintets and septets, which are like 6, 7 peaks in some cases. So this spin-spin coupling can give us valuable information about the connectivity of atoms in a molecule because it shows us which protons are close neighbors to which protons. So the structural information, so what are the structural information from features of a hydrogen NMR spectrum? So we can get information about the position of signals. So it indicates what types of hydrogen the molecule contains, and the number of signals, which indicates the number of different types of hydrogen in a molecule, and intensity of signals indicates the relative amounts of each kind of hydrogen in the molecule, and spin-spin splitting of signals, it gives further information of the neighboring environment for various hydrogens in the molecule. So here's an example of the hydrogen NMR spectrum. So an NMR spectrum is a plot of the intensity of a peak against the chemical shift, which is measured in parts per million, ppm. Now what is a chemical shift? So the chemical shift of a carbon-hydrogen bond increases with increasing alkyl substitution or electronegative atoms attached. For example, here we could see that with increasing number of alkyl groups R1, R2, R3, the chemical shift value also increases. So the absorption of alkane hydrogens occur at a relatively high field. So hydrogens close to an electron withdrawing group like halogens or oxygen are shifted relatively lower field, which means that they are de-shielding. So the more electronegative the atom, the more the de-shielded methyl hydrogens are relative to methane. So here's a table with values for chemical shift for each group. So with the fluoride group, the chemical shift would be 4.26 of the CH3, and with iodine it would be 2.16. In a magnetic field, the electrons of a carbon-carbon triple bond are induced to circulate, but in this case the induced magnetic field opposes the applied magnetic field B0, like we already saw. So the proton thus feels a weaker magnetic field, so a lower frequency is needed for resonance. So the nucleus is shielded, and so the absorption is higher. So you don't have to remember like for which kind of molecules and which interactions what the value of the chemical shift is. So you already would have a standard table for that, which tells, like for example, for benzene attached with the hydrogen atom, the chemical shift would be something between 6.5 to 8. So yeah, you just have to look up those values, and based on the position of the peaks you can identify which molecule is present, which atoms are present, and how they're arranged. So here's an example. Like we said, the benzene ring attached with hydrogen, it's highly de-shielded, and the chemical shift would be 6.5 to 8 parts per million. Whereas the C triple bond C attached to a hydrogen is shielded, and its chemical shift would be lower with 2.5 ppm. Now, if you have a look at the carbon NMR spectrum, so these are easier to analyze than the hydrogen spectra because the signal splitting can be avoided, because carbons cannot be very close to each other, as close as like hydrogen. So H3 would be 3 hydrogens that are close to each other. So that would not be the case with carbon. So each type of carbon atoms appears as a single peak with one hydrogen decoupling. So let's now first look at a simple example of how to interpret the NMR spectrum. So to interpret the NMR spectrum, we need to use a method that will help us to systematically first understand the context, what do we already know about the molecule, and then how many different proton environments are there in the molecule. And for each proton environment, what can the chemical shift tell us, how many protons are there in the environment, and what are the splitting patterns tell us about the number of protons on adjacent carbons. So we start by looking at the context. What do we already know about the molecule? So in this case, the question would tell us that the molecule, it's an ester. We know this, and we also know that this is a proton NMR spectrum because the chemical shift scale, the scale on the x-axis, is from 1 to 0 to 11 parts per million. So in case of carbon 13 NMR spectrum, it would be up to like 200 ppm. Looking at how many clusters of peaks are there, that would tell us about how many proton environments are there. So here we could clearly see that there are 1, 2, and 3 proton environments which are labeled A, B, and C. Now we need to have a look at the chemical shift for each of these environments. So peak A has a chemical shift of 3.7. If you look at the x-axis, it has 3.7 ppm. And if you look at the NMR data sheet, you'll see that an environment with 3.7 ppm is a proton, a hydrogen on a carbon connected to an oxygen atom. And then peak B is at 2.4 ppm. So that is a hydrogen on a carbon connected to a carbonyl group, that is C double bond O. And then finally peak C is a hydrogen connected to a carbon that's part of an alkyl group. Next, we need to use the area information. This is the area under each peak, and it tells us how many protons are in that environment.
So these numbers are generated by the instrument. So it calculates the area under each peak and it gives us the number near each environment. So here there in for peak A there are three identical hydrogens in the environment that makes a CH3 group next to an oxygen. And there are two protons in environment B. So there's a CH2 group near to the carbon, and there are three protons in environment C. So that is an alkyl methyl group. So we have got a list of all the fragments of our molecule. And now we just have to put together all these fragments. So this is where the splitting of the peak helps because it tells us the sequence of the pieces. So peak A is a singlet, so there is no carbon connected to the carbon with the hydrogens for peak A that has a hydrogen on it. So no hydrogen on the adjacent carbon, and that fits with an oxygen being connected to that carbon. So peak B is a quartet that tells us there are three hydrogens on the carbon adjacent to this. So it's looking very much like the methyl group here is connected to the CH2 here, and it's confirmed because environment C is a triplet, which tells us that there are two hydrogens on the adjacent carbon, and that signature of a triplet and a quartet linked to each other is very characteristic of an ethyl group. So now we have all the information necessary to map out the structure of the molecule. So we have the methyl group, and then the oxygen, then the carbon, and then an ethyl group. So this is methyl propanoid, and we just label which protons are responsible for which environment in our molecule, and we can see that it's all consistent. So again, just looking at the structure, this CH3, this R group would be connected to a carbon with two hydrogen molecules. So you just flip this around. So this carbon is connected to this carbon CH2 and C double bond O, and this carbon is connected to this oxygen. So O, and we have this group over here. So this is how you read an NMR spectrum and identify what molecule the compound is. So the UV spectroscopy or the UV visible spectroscopy is generally used to find concentration of different substances or compounds in mixtures. It can also tell us about the chemical groups, but the data is not very reliable. So also this method also uses kinetic study in enzymatic activity. So usually in a UV visible spectrophotometer, you will just be having a single beam, and in that case, like you first have to get the reading of a reference, which is usually water or any colorless solution that does not have any absorbance, that does not uh, absorb any wavelength of light. So we do that, and then we replace it with our samples of different dilutions or whatever, and then we take readings for those in the same machine. But here is a schematic of a double beam UV visible spectrophotometer. So it has a light source and then a monochromator or a beam splitter that splits the light into two beams. So one passes through the sample and one passes through the reference, and the transmitted light is then recorded in a detector. So the advantage of this double beam UV spectrophotometer is that you don't have to like first get the reading of a reference and then replace it with a sample. So you could just do it together. So the detectors could be photodiodes, PMT, or photomultipliers, while the monochromator, it consists of two slits, one prism, and the first slit uh, emits the light onto the prism, while the second slit allows one wavelength of light to pass in through the sample. And then there's a cuvette. So cuvette is usually a glass container where you pour your samples and fit it into the machine to record your transmitted light absorbance. So the the Q, like usually the samples are organic compounds of proteins, and so you have to set the wavelength of light before you use the spectrophotometer. So usually proteins, they absorb wavelength of 260 nanometers, whereas nucleic acids like DNA and RNA, they absorb wavelength of 240 nanometers. So for protein samples, you usually set 260 nanometers. So if there's a high concentration of protein, the absorption also will be high, and less intensity of light will be reflected, so the transmittance would be low if the protein concentration is high. So transmittance is inversely proportional to absorbance. So also transmittance, like we just saw, it depends on the concentration of the molecule. So to convert a value from percentage transmittance to absorbance, we use the following equation. Absorbance is equal to 2 minus log of percentage transmittance. So also we have, with from Beer-Lambert's law, we have A is equal to epsilon Cl, where A is the absorbance, epsilon is the molar coefficient, and C is the concentration, and L is the path length. So if we know the concentration and the path length and the molar extinction coefficient, we can calculate the absorbance from that equation. And yeah, any value that we know, we can just rearrange the equation and identify the other value. So, while mass spectrometry, UV spectroscopy, and circular dichroism spectroscopy are all powerful techniques for studying proteins, they have limitations when it comes to determining the tertiary structure of proteins, especially in cases involving secondary structures like alpha helices and beta strands. So, here are some reasons why these three techniques have limitations for analyzing the tertiary structure of proteins. So, in case of mass spectrometry, the limitation is that mass spectrometry is excellent for determining the mass and identifying the composition of peptides and proteins, but it primarily provides information about the primary structure of the proteins, which is the sequence structure, and to some extent the secondary structure. So, mass spectrometry is not inherently well suited for providing detailed information about the 3D arrangement of atoms in a proteins. It is more commonly used for studying protein folding, modifications, and interactions. And then UV spectroscopy. So, this is sensitive to the absorbance of aromatic amino acids like tryptophan, tyrosine, and phenylalanine, and peptide bonds, and it provides information about the protein concentration and the secondary structure element. So, it's used for quantification mostly. And so, UV spectroscopy does not provide direct information about the tertiary structure of the protein. It lacks the resolution to distinguish between different spatial arrangements of secondary structure elements. And then CD spectroscopy is widely used to study the secondary structure of proteins by measuring the differential absorption of the left and right circularly polarized light. So, based on this difference, you would get to know whether there's an elliptical structure or not in the protein sequence, and different secondary structures like helices and beta sheets, they have a certain pattern for these elliptical structures. So based on that, using the circular CD spec readings, we would get to know what is the secondary structure of the protein. So while CD can provide insights into the overall secondary structure content, it does not offer detailed information about the specific 3D arrangement of these elements in the tertiary structure. So, in contrast to these three methods, NMR spectroscopy is particularly powerful for studying the tertiary structure of proteins in a solution, providing information about atomic level details, including the arrangement of these alpha helices, beta strands, and other structural elements. The ability of NMR to probe proteins in their native environments, which is the solution state, and to provide dynamic information makes it a valuable tool for structural biology. So now coming back to the question, we just saw that nuclear magnetic resonance (NMR) spectroscopy can is used to determine the tertiary structure of protein consisting of alpha helices and beta strands, while the other three maybe good for secondary structure and primary structure, or maybe the quantification of proteins, but not for the tertiary structure determination.